So every time after the Big Bang and every chi value, all chi values at a given time that are within the cosmological event horizon. So this is the set of all eventually observable events. If you don't have an inflationary cosmology, this set represents all space-time points. Fantastic. Other than the Big Bang itself. This is open there, so you don't get to see it. Okay. The last lemma is really technical, and want to get to a few other things and questions. So, but what it does is it says that you have a coordinate transformation from tau sigma, which are, I think of as almost Fermi coordinates, to the t chi coordinates. That you have a diffeomorphism, and it uses all the lemmas we established before to get that. And so, where is this transformation valid? It's going to be on the set of analogous set of positive Fermi time values and rho values that are within the radius of the Fermi space slice. And so, as I mentioned, you can convert from sigma to rho. And here's the thing I said that it was easy to get from tau sigma to tau rho coordinates. You define these guys, and they're all smooth functions, so then you have this diffeomorphism with an inverse, and then you define this, and that's your transformation to tau rho coordinates. And so it goes from the set of all observable events, that V, to that physically meaningful set of all positive time values, where the distance is within the radius of the Fermi space slice. Okay, so the theorem that we were after, that all those lemmas put together, more or less there was one other thing in there, which is that the Jacobian determinant of the coordinate transformation we were looking at is positive, provided that d chi d tau is positive. And we showed d chi d tau is positive. So that was really the only other step in this. So here we get what I was saying, which is that you have Fermi coordinates and the transformation's valid in V. So Fermi coordinates extend to the cosmological event horizon. It's a really cool result that says you have a coordinate transformation that's valid not everywhere, but everywhere that you could possibly care about because it's everywhere you could ever observe. Okay, and then direct, this guy doesn't fit in the box exactly, but direct computation shows that the metric in these coordinates is as follows. This is nice, there's no coefficient there, but the coefficient for the time coordinate is messy. In 2 dimensions, you can ignore the stuff after the second addition sign. Okay, so, all right, 2 examples that I would like to get to, so there's some physical interpretations happening. The Milne universe is a prototype universe with no matter or energy, negative spatial curvature, and a of t equals t to the 1 expansion rate. It's instructive as an expansion. It's a good, I mean, when you think of expansion, a of t equals t seems like an expanding universe, so it's a good prototype. You can compute directly the cosmological event horizon. It's infinite. That means all points are within it, which means that as Dr. Klein and Evan Randall show that the coordinate transformation is global. Right, Fermi coordinates are global, and the transformation is actually nice. There's no integrals and stuff. So this is how you convert from t chi Robertson-Walker coordinates to tau rho Fermi coordinates. And that horrible expression for g tau tau, sorry, going back to it actually. If you look, you do 1 minus alpha right here, and alpha is 1 for the Milne universe, so everything past that addition sign goes away. This sigma goes away, so you just get minus 1 over 1, and you get that whole thing is just minus 1. And so the metric is this, which is the Minkowski metric. So local coordinates are static. So there's this interesting thing going on where a dot is positive, which I called expanding without anyone being like, wait a sec, that doesn't seem like expanding, because it does seem like expansion. But now in local coordinates, there doesn't appear to be expansion going on. And so, there's from what I got out of reading the research, it seems like some people feel like you just can't talk about almost anything in general relativity because so many notions at least appear to be coordinate dependent, and so maybe it's just, so do we say it's not expanding? Do we say it is expanding? Or do we just say, like, expansion's not a physically meaningful concept anymore, and all you can talk about are redshifts because those are observable? I would say, remember this equation where we find the radius of a Fermi space slice? In the Milne universe, the gamma functions, everything goes away. So you just get the radius, in the units we're using at least, is just exactly 10. So what you could arguably call the radius of the universe is an increasing function. So in that regard, in that regard, I would say that you could argue that the Milne universe is expanding, and that this function that could be argued to be the proper radius of the universe is an increasing function of time. And when you say that, that sounds like an expanding universe. Okay, so you asked Dr. Siddharaman if there is any research about power law cosmologies. So this is a paper where the authors suggest a model based on observation, which k is -1 and t is t to the alpha, with alpha somewhere in that interval. The authors are Zhu, Hu, Lu alkenes, and so in my thesis I refer to it as the Zahula universe, just because, I don't know, I didn't want to write Zhu, Hu, Lu alkenes over and over, and I hope that name catches on. For definitiveness and comparison with those models I mentioned at the beginning, t to the 1/2 and t to the 2/3, 8/7 falls nicely in between 1.09 and 1.19, so k equals -1, t to the 8/7, I am coining the term the Zahula universe. And one thing that is interesting to note is that the proper radius of a Fermi space slice, when alpha is 8/7, so bigger than 1. So now we have an inflationary universe, a universe that is expanding faster than the Milne universe. You get that its proper radius as a function of time is about this, which is less than what it was in the Milne case, which is really counterintuitive, I would say. The universe is getting bigger faster, except its radius is not getting bigger faster, whatever that means. So that motivates taking a limit. Well, what if, as alpha gets bigger, what happens? The limit goes to 0. So the faster your universe is inflating, the smaller its radius is at a fixed time. So
this kind of reminds me of the volume of an n sphere in n dimensions. As n goes to infinity, the volume goes down to 0.
Oh, that does sound a lot like that, yeah. Here's 3 examples, so a proof, right? But so all I'd say, like, you've got your proper radius of the universe being this as you cut across, and you notice that the smaller alpha is, the wider it is, that is, the bigger the radius of the universe. And so this thing just keeps on, the cone just keeps going like this as alpha goes to infinity. So what could this possibly mean, is what I've been thinking about for, trying to write my conclusion. My goal was to interpret this in some way. So to remind you, this came from setting Ts equal to 0 in this, and Ts equal to 0 is the Big Bang. So I said this earlier,